Okay, then let's talk about the inverter-based switch capacitor integrator. Because we have only this inverter instead of OTA, so it will reduce power significantly, all right? So I have some switches, and then those thermal noise will be determined by something like that. This should be CS, okay? Something like that, mostly. So this is RMS noise voltage for thermal noise, okay? So to reduce noise, input noise, I have to increase this capacitance, right? And then see here, actually, we can implement the same thing here. See, if you compare this one in the previous case, see, this is that is that by 2, and there is something like that by 1, right? Yeah, this is gain stage. So if I eliminate this thing, then it becomes integrator, okay? So in this version, we just implemented like that, all right? Yeah, see. So during this is non-inverting. Yeah, see, you can see during by 1 phase, this charge will be developed there, right? So this voltage will be that logic threshold voltage. This is rep, the same as logic threshold voltage. This inverter will be grounded. 3.3. So this node is actually virtual ground. You can see this is some virtual ground of op-amp, say something like that. This is just similar to that virtual ground of VG, and this thing is some rev or something like that. This inverter works similarly to this OTA conceptually. Yeah, so if I don't reset by this by 1 switch, if I don't reset this feedback capacitor by 1, say if I eliminate this by 1 switch, it works as a switch capacitor integrator. Okay? Yeah, question? Yeah, it will have something like that transfer function. Because V1 is sampled at the phi 1, but generate the output during phi 2, I have a half t delay. Yeah, if I want to make a inverting integrator, you will need an inverting integrator, right? In your homework. So this should be phi 2 and the phi 1. Yeah, so then it will be inverting integrator. Okay? Okay, let's just simulate this part. Oh yeah, actually we have some code here. Let's look at the code first. Okay, code first. Let's just see. The only difference is this part, that switch, by 1 switch is commented out. This S5 switch. Yeah. This S5 switch was used in the gain stage, but that S5 stage is this one. This is CF, this thing is by 2. Yeah, that thing is the S6 switch, right? S6 switch, this is VO. S6 switch is there. but S5 switch is, let's just see. Yeah, this is something like that. This is CC. How do I connect this one? I think this is connected, right? What is CFVG? Yeah, it's connected to virtual ground there. Okay. And this thing is by 1, something like that. So, S5 switch is gone, commented out. Okay. This is by 1 switch. Then it becomes just integrator. All right? So let's just see. Is this sub-circuit? Oh, yeah, this is a sub-circuit. How come I make this sub-circuit? Input VO prime. Yeah, VO prime is there, right? This thing is sampled by another by 2 switch. So this is the VO prime, right? VO prime. Okay, there is some reference node, all those switches, supply voltage, all right? Then let's just see. How come I have 2 sub-circuits, but I have a different input? Oh, yeah. Because I want to change a certain frequency, right? One is 100 Hz, one is 1 kilohertz. So I have a 2 switch capacitor integrator. Switch capacitor integrator with the input of one is in1, O1, OP1 into OP2. So here, see, I used 100 Hz sine wave. This is 1 kilohertz sine wave input there, right? Okay, let's look at the output. I think it's there, right? This integrator. Okay, simulate. Graph. So this is my input. So I have 2 inputs, right? 100 Hz, 100 kilohertz. So this is my output. Output is distorted. All right. So you can see this sky blue one is 1,000 Hz, 1 kilohertz output, and this thing is 100 Hz output. It looks like integrator. Gain is not exactly 10 times, right? Gain is only around twice or something like that. So if you compare, let's just say because this is a pretty large, so I have a large distortion. If we use a differential structure, a differential stage, this is a single-ended integrator. So I have a large distortion. Differential version will reduce this distortion. Okay. So if you compare this one, let's look at the phase relation for this 1 kilohertz stop. So 1 kilohertz stop is this red one, and then this sky blue one. You can see 90-degree phase shift, right? Phase is exactly 90-degree shifted. Any question? Oh, even more complex. Differential version. See, if you look at differential version, it's basically same as a single-ended version. If you see this part, where is my virtual ground here? Oh yeah, here. That part, this exactly same as the previous single-ended version, right? So you can see exactly same copy here with a different, this is a P, M, and then you can see exactly same version there. Okay? Same version. Then I have this part is also same. Just copy. There is a common mode feedback. So those VOP, VOM is there. This is VOM, VOP, and then those are all lab, right? VLT. Say there is this virtual ground, right? So there is a switch capacitor. This looks like a VOP, VOM, and then see I generate that average of VOP, VOM that is connected to this amplifier, inverter amplifier, right? So it will be a negative feedback for the common mode signal, all right? Yeah. Ooh, homework. Another week, okay? This will be the last homework. So yeah, this is just a low pass filter, second order, by using inverters and switches, ideal switches, S. Okay. So I think that you can refer homework number 8. In the homework number 8, you generated a switch capacitor low pass filter, second order one, right? You just convert that one into inverter version. And then, yeah, so you just repeat it, compare bandwidth with the spec. Yeah, this is your spec. And fully differential second order switch capacitor filter. And then, yeah, repeat 2 and 3. Question? Yeah, this is active RC version of that low pass filter, second order low pass filter. Yeah, you just replace those resistors by switch the capacitor. However, you need only use 2 inverters there, not 3. So here, see, you need to use 2 inverters only. So you can invert the polarity by using switches, right? So this part must be eliminated. Question? No? Okay, let's try to simulate this part. Okay, do I have a, let's see. We may edit a little bit. This is not this homework, just this part. Okay, can I switch this one? Can I sweep? No? Oh yeah, I can make it. All right. Yeah, see, this is, see, we want to make a pseudo-differential. So we can say a fully differential switch capacitor integrator using inverters, okay? Then, I mean, this circuit. We want to implement this circuit, okay? Say, those are the same. You know, this part is the same. The only thing left is this part. We need 4 more switches and 2 more capacitors. Okay, so let's see. This is VOP and VOM. This is VOP and VOM, right? And this is red. Okay. See, let's just see. Do we have a correct version? See, this is your inverter sub-circuit, inverter 10 sub-circuit, and then this is my integrator. Okay. Yeah, all the same. So here, see, I need a more node in this sub-circuit. See, I have what? Input actually its own input. So this sub-circuit is actually this part. I want to make this part one sub-circuit, okay? This part, this half. And then, yeah, so I will call two sub-circuit cores with a different input, BIP, BOP, and the BIM, BOM. Okay, so I can just add four switches and two capacitors, right? Virtual ground. So I need to generate, this is N4, this node will be N5. So this is REF, this is some BOP, BOM or something like that, okay? So let's see whether I can make it or not. See, where is my, oops, not this one. Maybe we can add it here. Can I make it larger? Nope. Can I, oops. Can I make it larger? Oh, I cannot make it larger. Okay, let's look at the PowerPoint then. Let's see, where is my, oh yeah, here. Now all the same, I can, oops. I can add oh, I see. This sub-circuit name is, so I want to make this sub-circuit name oops. Okay. This is DIFF. And then let's see. Do I have four switches? Yeah, I have two capacitors here, right? VG, virtual ground, M4. Okay. Do I have four switches here? Oh yeah, I have four switches. N4VO, M5VO, VO inverter. This is the opposite one. VO inverter by 2, VO REF. Looks like I have everything, right? So let's see, where is my sub-circuit core? Let's see, X3. Yeah, I just make this is a differential. Then I need input. What's my input? Input is in 1, in 2, right? So where is my input? Oh yeah, here, in 1, in 2. So let's see, this is no good. I need the same thing, right? Oh. So I have a plus 50 millivolt, a minus 50 millivolt. So I want to generate a differential output. I have to print out those things. What is output? Output is actually OP1, OP2, right? OP1, OP2, VOP, VOM. Okay, in 1. OP1, OP2. OP, VOP. It is VOP? Yeah, VOP. This is the internal output, right? Before sampling by 2. Okay, let's try to simulate this one. I will copy all those things into Spice netlist here. Oops. Yeah, do I have that one here? Yeah, differential looks like this is, this looks the new one, right? Is this a new one? Yeah, it is a new one. Okay, let's try. Oh, somehow it's very good. It works. Okay, differential. Oh yeah, this is differential. So my input is there. Yeah, I have a differential input. I have a differential output, OP1, OP2. Is this a differential? Yeah, good. Very good, right? Excellent. How come it works for the first time? It never happens, eh? Let's see. I expand this part. So my differential output looks fine, right? It's a 90-degree phase shift already. Okay? Yeah, question? Oh, I hope you enjoy last homework. No? Yeah. Any question about the homework? Hmm? Okay, then I think you don't have any problem with this homework. Okay, let's finish, okay?